Okay, hello everyone. This is a tutorial on how to use the OpenRocket software for designing and simulating rocket designs. To start off, you're going to want to go to openrocket.info and go to the downloads page. Select whatever your operating system is, and it will open up a little file that contains the application. In macOS, you just drag this and drop it. I already have installed, so we'll just reinstall it. We can inject that. We can delete that. So let's start with opening up OpenRocket. Now, these controls may seem a little bit weird, but after about a day or so of experimentation and messing around, you'll get the hang of it. These are all the parts that you can put on. Only certain ones you can start with. So we'll start with the body tube of our rocket. It'll give you a whole bunch of pre-made ones that you can select from, but we can create our own. Let's say the most reasonably sized rocket engines that we'll be using will be around 1.8 centimeters in diameter, so we'll design our rocket to be a bit wider than that on the inside. Maybe 3. Then our diameter can be like 3.4, I guess. Then the length, we can choose the length. This changes the units. Set to 20 centimeters. You can change the zoom with these 2 buttons here. And you can rotate it like this. It's not going to show any difference though, because you're just looking at the side of a cylinder, which is, still a cylinder. Now let's figure out how we're going to get an engine into here first. Of course, an engine goes inside of the engine block, which is represented with this inner tube part, but the inner tube must be held in place with a centering ring. In the Estes Alpha 3 that most of us participated in building, well, some of us did, these centering rings were the little green parts that went inside the fin segment. Centering ring 1, inner diameter 1 to be 1.8 centimeters. And what's the inner diameter of this one again? 3 centimeters. We'll keep us at like 2. Oh no, it's okay. It's on the outer edge. So if you double click on any part, you can change where it is with this little slider here. Or you can enter the number in manually. Now we'll need a second to hold the engine block in place, so we can copy that and paste it. Rename the second one to engine 2. We can move it up a little bit. Within the body tube, we can now add our engine block, our inner tube. I'll go back and move this one to be near the top. This rocket looks a bit short. I'm gonna make it a bit longer. Okay, and now we can add some fins to the side. We'll get to the nose last. Let's do freeform, because this allows us to make it whatever shape we want. See, this changes the fin shape. That, whatever. It's about time I mentioned something else. This is this blue dot is called the center of gravity. It is where the rocket balances around. You know, if you had the rocket in your hands, it would you would literally balance it by here. You put your finger under this point and it'll balance. This is called the center of pressure. It is where all the air will be pushing, well, the average location of it, which is calculated by the software automatically. Now, so basically, any force, as long as the rocket's moving, any force that from the air that hits the rocket will act from here and around here. Think of it as a lever, where this is the pivot point, and you're pushing around here. Let's go back to making our fins. I want our fin to be shaped kind of like this, but I can't make a straight line. I see at this point is at X and Y points there. So we can set the Y point to 2.47. There we go. I can see the view thing does allow you to see through parts of the rocket. You can also change how many fins you have. We can have 8,000 fins. Sorry, just 8 fins. I don't think you'll need more than that if you're designing anything that isn't a literal military mortar. You can have 1 fin as well. This is where you move it. This is just saying along which part of the body it should be placed. I'm reasonably sure that this is basically just some structural reinforcement that you can put onto the base of the fin. Fin can't. This twists your fins. It's like rifling on a gun, because the fins being twisted makes the rocket fly spinning, which allows it to stay more stable, like how a bullet fired from a gun stays more stable if it has rifling. It essentially turns the whole thing into a gyroscope. Okay. Now if we go back up to the sustainer, which is basically just the stage of the rocket that we're operating on, we can now add our nose cone. Now you'll notice that the nose cone is behind the rocket. That is not good. You want the pointy end this way, because this way is the front of the rocket. Well, this is the front. Then the way that OpenRocket works, front, down, and as you go further down in this little section, you get further to the back. So you can click and drag the part to the front. Now this gives me a warning because the nose cone and the body tube are different diameters. Let's see what the outer diameter of the body tube is. 3.4 centimeters. Let's see what the nose cone is. 5 centimeters. There we go. Now we'll also want to add a shoulder. It's a little part of the part of the nose cone that goes inside of the body tube. This lets it be a bit more stable. We want this to be close to the inner diameter of the body tube, so it's nice and snug. Inner diameter is 3 centimeters, so that's like 2.9. There we go. Okay, so that's most of our rocket done, but we still need parachutes, shock cords, and a little thing to simulate wadding. Parachute, you can go with a pre-made parachute. You can sort each item by different aspects. Sort by diameter. You can sort by how many sides it has, how many lines are connecting it, how long the parachute lines are, and what material it is. Or even who makes it. Let's go with the Nestus chute. 61 centimeters, that's kind of big for this rocket. And check the name for stuff as well. 12 inch and 18 inch, these. Oh, this one. They seem to be identical in specs. Now, you'll notice that the parachute is in front of the rocket. That happens later in the flight, not now. So we can make it near the bottom of the parent component, which is the nose cone. Set to 0 inches, 0 centimeters above the bottom of the nose cone. Now, we'll also need a shock cord to keep the nose cone from flying off of the body completely when the parachute ejects. You can change how big you expect it to be when it's packed. Great. But there's one last thing. When the ejection charge fires off, that's gonna, send out gas up here. So, we need wadding, which comes in the form of a mass component, which is just a useless. There's nothing here, it just has mass. We'll put it in the middle. And change how much wadding we have. It doesn't really care about wadding. This software only just uses it to see the mass of the rocket to do calculations for height and stuff. That looks good. And move the mass up like. Let's put 15 grams of wadding on here. Now we're almost ready to run it through simulations. We just have to tell the simulator, hey, we want this engine placed here. We want the engine placed in the inner tube, which is the engine mount. Then I want to click New Configuration. Now you can select whatever engine you want. Let's just shove a C6 on here. These are mostly just classifications. U. No C65s. Actually not. We can go even more powerful. Let's go with a D-class engine. D-class motor. Oh wait, no. They already have the impulse thing here, so I can just limit the range down to this D-class. 20 Newton seconds. Looks like it's a bit wider than I thought it would be, so let's get a different Not you. There we go, that's nice and snug. Now we can go to flight simulations. Move these lines around. I can see all the data. I prefer to just click this button just in case. Let's go through each of these. Velocity off-rod is how fast the rocket will be traveling off of the launch pad. Apogee is the highest point of flight. Velocity at deployment is how fast it'll be going when the parachute is deployed into the air. You want this to be really low because you don't want the chute to be yanked off, basically. Optimum delay is like what it thinks that the best time delay between when the engine cutoff happens and the parachute ejects should be. Maximum velocity, maximum acceleration, time to apogee, how long it takes to get to here, the flight time, how long it takes to get back down. Ground hit velocity is how hard it thinks that the rocket will hit the ground. Now, our configuration has a 5-second time delay, but it's saying that the optimum delay would be 6.3. So let's adjust our simulation to be, let's adjust our engine to reflect that. Hello. I gotta click here, okay. Closest that we have is 7 seconds, so we'll go with that. Look at that, it got slightly higher. And it's also deploying the parachute in slightly lower velocities, which means that it'll have less of a yank on it. So that's good. Also, you might have noticed that each, where was it? Simulation has different launch conditions. You can just hear. Let's go through these. I don't mess with these. Well, time step I know is like it's like the resolution of the thing, of the simulation. You can export all of these into a CSV file that you can open with the spreadsheet software. This one I like to look at. This is off by default. This is the plotting tool. It lets you look at information over time. You have motor ignition, which happens at 0 seconds, I think. Vertical acceleration, I think this is vertical velocity. Okay, yeah. You can hover your mouse over here. Then you can also oh, there it is. You can zoom in and out by making squares where you want to see. Enhance this section. Let's look at the time from motor ignition to apogee. Show me the full thing. This supposed to be what the CSV files are for. There we go. So as you can see, vertical acceleration goes up. And it starts to decline as the engine goes out. And engine goes out here, it goes to absolute minimum. This is vertical velocity, how fast upward it's going. This is altitude. Goes all the way up here. You can export the image as well. Let's say this simulation result. If you really want to look at the fine details, you can export all the raw data in the CSV format, which is exactly what it sounds like. It's data separated by commas. Whoa. At the byte level. Here, let me show you. See, commas. Spreadsheet software does a nice job of just putting it into a table. Now you want to save your design as well into a file. This can be done with File, Save, or just Command S. Fill in these fields. My keyboard cover came off. There we go. And save a file to save it to Rocket. There. It will be saved to these files, these orc files. OpenRocket. Now you can close it. Open it. Close it again. You can email these files. They're pretty small. So yeah, that's how you use OpenRocket.